lecture 2. So I still have a few things to continue from the first lecture about just properties of, some basic comments about properties of interstellar clouds and the environments in which interstellar molecules live. And then I'm going to try to go very, very quickly through an introduction to radiative transfer as it applies to the quantitative spectroscopy that we do in astronomy. The first, since Susanna was showing beautiful pictures of telescopes yesterday, I wanted to show some of mine. These are actually the telescopes that sit where I live and have worked for a couple of decades. On the west coast of Sweden, in fact, very much on the coast. The antennas are within sight of the water. This is actually a real picture of the 20-meter antenna, millimeter wave radio telescope inside the radome when the radome was replaced a couple of years ago. So there was a brief opportunity when one could actually get a clear, simple picture of the telescope, the whole telescope, by looking in through the exposed top of the radome. We also have an antique 25-meter telescope that is still used. It was installed in 1963. Is still used for very long baseline interferometry experiments. And two brand new smaller antennas that are used for geodesy, Earth measurements, using actually astronomical sources, quasars, distant quasars, as an inertial reference frame for reckoning the shape, size, motion of features on the Earth. And in fact, by doing interferometry over intercontinental baselines over many years, the first such intercontinental interferometry experiments were carried out between this telescope and a telescope in Massachusetts. And that was in 1968, was it? In any case, over that timeline, it's been possible through these radio astronomy techniques to measure directly the continental drift. You can actually see the time change, the rate of change of the path difference between the two telescopes. These are actually satellite antennas that have been set up with nice radio astronomy receivers, and these can be used by school classes over the internet, and there are school groups from all over the world that have used these telescopes through our education and outreach activities. And then this is one of the LOFAR stations, low frequency array. But I should dwell on that as a little bit of a sideline point. Okay, also, in his first lecture, Mike did a very nice introduction to the history of astrochemistry. And for a couple of reasons, I wanted to add my own historical chapter. One of the reasons is just to assert that radio astronomy is not the only way of studying interstellar molecules. That visible, infrared, and ultraviolet spectroscopy also have niche roles that can be very important. And here, I would say actually this is historically in our field of astrochemistry, this is an extremely important discovery. The hydrogen molecule. Now, it was not a surprising discovery because already in 1970, 50 years ago when this happened, it was not unexpected that there would be a large amount of easily detectable H2 if you could get an ultraviolet spectrum above the Earth's atmosphere. Well, George Carruthers was the first one to do it. And I think this paper is remarkable for several reasons. This is actually the data record, and that's the lower spectrum image. Looks a bit faint, and on top of that is a laboratory absorption cell spectrum, and the laboratory spectrum was actually recorded with the same instrument that later flew on rocket up above the atmosphere. So in fact, this short discovery paper also reports you might say, a laboratory astrophysics contribution as well. This is remarkable because George Carruthers, invented the UV detector that was used. He designed and built the instrument and the rocket payload, got the funding to have this mission carried out, analyzed the data, took the lab spectra for comparison, and got the right answer. Even from what looks like a relatively crude spectrum here, he got the right answer for the column density of H2 and something about the distribution of the H2 among its rotational states. This was later confirmed in great detail with the Copernicus satellite spectrometer 3 years later. So, for all of these reasons, I think it's really important to remember this is an historically important contribution. And here's just a little bit more information from the discovery paper. And I also dug out a picture of George Carruthers. He's the shorter, older gentleman. And this is a picture from about the time when he carried out this rocket experiment. Okay, but back to interstellar clouds. Actually, the sort of cartoon concept of an interstellar cloud has to be flexible because the conditions may vary. And just one point I wanted to make is that we can imagine a cloud of gas, this dark blob in the center of the cartoon, sitting in the space between stars. And in the neighborhood of our sun, that is where we live in the Milky Way galaxy, the typical distance between stars is of the order of 1 parsec, a little more than 3 light years apart. And so an interstellar cloud that's a few tenths of a parsec across fits easily in the space between the stars. On the other hand, if we consider interstellar matter in the central molecular zone of the Milky Way galaxy, the central 100 or 200 parsecs of our galaxy, the stellar density is so high that for a similar sized interstellar cloud, statistically we would expect it actually to contain a large number of stars. So even our cartoon concept of interstellar clouds needs to be flexible. Now, I put this up actually. This is a very old result from when Buell-Januzzi was just a first or second year graduate student. This is the result of a project that he did together with me and Van Dissuk in the 1980s. Buell-Januzzi is now the director of Stewart Observatory at the University of Arizona. In any case, the reason this is interesting is that this interstellar cloud was not found by blind survey mapping of the carbon monoxide emission line in the galactic plane. Rather, this cloud was first identified by visible wavelength absorption spectroscopy toward a star at this position on the map. So these are coordinates on the sky offset from the stellar position. And so we already knew that there was a large concentration of atoms and molecules in this direction, and thought it would be fun to see if we could actually map out a structure that might have closed contours and signify a cloud by using the carbon monoxide J = 1 to 0 rotational line in emission. And sure enough, there is. There seems to be a set of multiple peaks in the brightness of the CO and so on. But this is one example where one can actually do very complementary observations, optical absorption spectroscopy together with millimeter wave emission spectroscopy. Here's another way of visualizing an interstellar cloud. This is, I think, one of the most dramatic ones. This blank spot in the middle of the star field is actually a dark cloud. It's dark because of the dust particles that accompany the interstellar hydrogen and other molecules in the gas. And the dust particles are extremely effective at absorbing and scattering visible and even more ultraviolet light. This extinction of light is wavelength dependent. And so it's very strong at short wavelengths, much less strong at longer wavelengths. So as you go into the infrared, actually, you can start to see through this dark cloud. Okay, now, one of the things that I ran out of time to cover in the first lecture about the environment of cosmic molecules are the cosmic rays. And cosmic rays have been mentioned before in other lectures, but I wanted to just say a few more words. It's already been pointed out that because cosmic rays provide a penetrating way of ionizing hydrogen and helium, that there are some ions, even in dark, very thick interstellar clouds. The presence of these ions can start a much more rapid ion neutral chemistry that is more rapid at the microscopic sense, in the microscopic sense than a chemistry that would depend upon neutral reactions at low temperatures. Cosmic rays also provide some heating. The reason that even the darkest interstellar clouds have temperatures of 8 or 10 Kelvin rather than 2.7 Kelvin in equilibrium with the cosmic background radiation is because there is some deep heating as a result of the penetrating cosmic rays. So the electrons that are liberated when cosmic rays strike a molecule, and also the secondary electrons that come when those hot electrons collide with an additional molecule. The excess kinetic energy of the secondary electrons is the heating mechanism. The cosmic rays are charged particles. They're relativistic nuclei. Therefore, they do not, even though they travel at nearly the speed of light, they do not propagate in the way that electromagnetic radiation does. In the important sense that these charged particles are deflected by the large-scale magnetic fields in the Milky Way. There are naturally occurring magnetic forces in space. And so the interaction of the cosmic rays with the magnetic fields also constitute a form of pressure in the gas. And so this has some effect, maybe even very large effects on the dynamics of gas and how parcels of the gas collect, collapse, and form smaller structures like stars and planets. As we heard in one of the earlier lectures, cosmic rays can also drive a radiation chemistry inside ices, the frozen stuff on top of refractory dust particles. And for the dust particles themselves, cosmic rays can destroy or modify the properties of the dust particles. There's one other thing. Cosmic rays are so energetic, the ones with 100 gigavolts of energy per nucleon can do very interesting things. They can cause nuclear reactions to occur in the interstellar gas. And in particular, there's a process of the interaction of a cosmic ray proton with an ambient proton in a hydrogen molecule, if you like, that produces neutral pions. Pions decay in a characteristic way into a pair of gamma rays. And these gamma rays, it turns out, are actually detectable. They're astronomical signals. And here is an all-sky map from the Fermi Gamma Ray Space Telescope that shows the brightness of gamma ray emission. And there are point-like gamma ray sources. Most of those are active galactic nuclei, distant quasars. But the diffuse glow that you see here is mostly or almost all this pion decay process produced by cosmic ray interactions. And to the extent that these high-energy cosmic rays have a measurable, smooth, and predictable distribution around the galaxy, we can actually use the brightness of the gamma rays as an independent tracer of the total distribution of interstellar gas. All right, so that's just one other thing. And also, I'm nostalgic about this because one of the early wild things I got involved in as a student was the prediction that someday gamma rays through this process would be a way of seeing individual giant molecular clouds or cloud complexes, and so that dream has come true. Chemically, in the interstellar medium, this is one of the cycles that is instituted by cosmic ray interactions. Hydrogen atoms can be ionized by cosmic rays to form H+, which can undergo charge transfer with atomic oxygen to form O+. If that finds a hydrogen molecule, then it goes very rapidly and directly to OH+, which, depending on the molecular fraction of the material and the electron fraction, will either go on through additional steps with H2 to form H2O+ and H3O+, at which point it's saturated, or will recombine with an electron through dissociative recombination. Alternatively, this sequence of reactions can begin with the cosmic ray ionization of a hydrogen molecule to form H2+, which is the only molecule on this diagram that is not directly observed yet. I still have hopes. But every time a I'm going backwards. Well, roll the credits. Okay. That comment, in case you didn't hear it, it's a Microsoft product. What do you expect? Exit. Okay. It's a Microsoft product. I don't know how to exit it.
May I ask something in the...
Yes.
Yeah. So, Dr. I can't remember his name, sorry, but he had...
No, please, don't call me doctor, I'm Daniel.
Okay, Daniel.
You guys are our peers, you are scientists. You should call us by
you're
our
actually doing things.
Okay. So, Daniel had a really nice, like a chronology diagram from Big Bang to now, let's say. Where in this diagram would all of these reactions fit in? Like early, intermediate, like...
Oh, well, these certainly don't occur. Most of this doesn't occur early because there's no oxygen in the early universe.
Yeah.
That's all formed in stars and supernovae.
Are there dust?
This is taking place as we speak in the interstellar medium around us.
Okay.
Was that the question?
Yeah, that was a question.
Okay. In any case, the production of an ionization to form the hydrogen molecular ion, the very simplest molecule, in the presence of other H2 reacts on every collision with H2 to form H3+. In fact, that's actually quite interesting because the reactive collision rate is basically as large as the reactive collision rate is essentially the same magnitude as the elastic collision rate. So H2 plus formed in an ionization event doesn't really have time to become thermalized in any sense in the interstellar medium. Neither its vibration rotation population distribution nor even its kinetic motions. Yes.
So how big is the role cosmic ray playing in ionizing H and H2 here compared to other processes?
Okay, that's actually a very good question. Of course, far ultraviolet starlight, in principle, is able to ionize hydrogen. However, the hottest luminous stars also tend to be the very youngest ones. They're still surrounded by leftover gas and dust from their formation. So the ultraviolet light sources, typically, are surrounded by a region in which all of the ionizing radiation is actually trapped by the interstellar hydrogen atoms or molecules in the immediate neighborhood of the hot star. So what I'm trying to say is that the starlight ultraviolet source of ionization is often trapped within a rather sharp ionization boundary, surrounded by a fully ionized nebula, and then outside that is the rest of the the rest of the neutral interstellar medium, but all of the ionizing photons are basically used up close to the sources. The cosmic rays, the high energy cosmic rays, actually propagate around the entire Milky Way. On the other hand, it's only the low energy cosmic rays, meaning something of the order of 1 MeV per nucleon or less, that are effective in producing the interstellar ionization, but those still are capable of penetrating a fairly large stopping distance corresponding to column densities of the order of 10 to the 22 hydrogens per square centimeter. So comparable to the central thickness of a molecular cloud, even for some of the low energy cosmic rays. So the cosmic rays tend to be the most important penetrating source of ionization in the interstellar medium for hydrogen and helium. The other part of the story is that atoms, the neutral atoms that have ionization potentials smaller than that of hydrogen, are still exposed to extensive ultraviolet starlight, because the somewhat longer wavelength, less energetic ultraviolet starlight actually passes beyond the ionized zones of hydrogen and is capable of ionizing the elements with lower ionization potential. So for the carbon chemistry and the diffuse gas, where some UV light still penetrates, the ionization of the carbon is thought to be accomplished mainly by the ultraviolet photons that are not absorbed by H. Okay, well, one can analyze that extract of a chemical network very simply, and parts of it analytically under some conditions. And fortunately, with the launch of the Herschel Space Observatory in 2009, it became possible actually to observe many of these hydrides, interstellar hydrides, for the first time, the ones that have their lowest rotational transitions at sub-millimeter and far infrared wavelengths. And so several of the conclusions that could be drawn from that, especially through observations of these very reactive molecular ions. What was it that I've done it again. Let me just, I won't try to go back, I'll just summarize in words. These very reactive molecular ions predicted back in the 1970s already finally became directly observable. The predictions, to make a long story short, agreed generally rather well with the observations. In addition, it was possible, again as predicted, it was possible to use the observed abundances of these very reactive molecular ions to infer remotely the cosmic ray ionization rates in the diffuse molecular gas. And in particular, these could be studied most sensitively through absorption spectroscopy. And at submillimeter wavelengths, there are in the galactic plane star-forming regions that provide extremely bright background lamps for doing absorption spectroscopy of everything that lies between us and the star-forming region. Okay, so I wanted to lead on to show how the same sort of observation can be done in other galaxies, or at least to probe the interstellar matter in other galaxies. And ALMA, again, you've seen pictures of ALMA, is such a fantastically sensitive telescope that it's possible to observe quite a variety of interstellar molecules in the interstellar matter of the galaxies. And one example I've been involved with slightly, mainly in collaboration with Sebastian Muller at the Onslow Space Observatory, is to do a growing molecular census of interstellar matter at a redshift of 0.89. Now, to a chemist, that won't mean much. To an astronomer, that corresponds to more than half the look-back time to the Big Bang. That is, that's a long time ago. In fact, it's long enough time, 6 or 7 or 8 billion years of proper time back into the past, that one might start to expect evolutionary differences to start to show up in the elemental composition of the interstellar matter. For example, different isotope ratios, because the stellar processing of matter is not advanced, not as advanced in that distant galaxy as it is in our own galaxy now. And also the elemental abundances themselves might possibly be expected to be a little bit different. So that was part of the motivation for embarking on that. At this point, I think we have a list. It's been growing so rapidly that I don't remember exactly, but approximately 40 of the well-known interstellar molecules have been identified by millimeter wave absorption spectroscopy in this region. Just to give one example, one of the more recent ones, this exotic molecular ion, argon H+, is also now detected, identified in this redshifted absorber, where, again, the redshift is so large that the rest frequency of 617 gigahertz is shifted down to a convenient observing frequency for ALMA 339 gigahertz. Okay, and this just illustrates it.
When it's shifted that far, how are you positive you know what you're looking at?
That's an excellent question. Okay, the first molecule identified in this source was found by accident, and by finding a pattern of rotational transitions, then the identity could be established with 5 or 6 digit accuracy. And so we go searching for the redshifted frequency.
Okay.
When we're fortunate that we find something at exactly the right place. There are many other things to say about this, but the identification is done really correct.
So you know the redshift?
Yes, we know the redshift in this case very precisely.
Okay.
And it's the same redshift in essentially all of the molecules. We do see differences in the line shapes, and these are mostly kinematical differences that reflect, as in the case of circumstellar envelopes, that some of the molecules are located in slightly different regions of the path length through that galaxy, but very, very close to the average redshift. In this case, again, this is one of these sources where the foreground absorbing galaxy actually produces a gravitational lens that makes multiple images of the background source. And that's what we see here. There's a northeast component and a southwest component separated by approximately 1 arcsecond. And these are two of the lensed images of the background quasar, which is effectively a point source. There's also a very dim third component that doesn't show up at this frequency, but Sebastian Muller is currently analyzing some observations of the third lensed image at the moment. That's of interest for cosmological purposes. Okay, these are examples of what the spectrum look like. I really should race on to get beyond that. The source is so rich for us that finally some deuterium-containing molecules have shown up for the first time in this source, NH2D, ND, and so on. That's of interest for the astrochemistry as well.
John?
Yes?
What about argon deuterium plus? Would be the same source.
Right. In that case, I think
You don't have to.
so one thing about the deuterated molecules, this hasn't really been talked about here, is a very interesting aspect of interstellar chemistry. So I might as well add a footnote. So I'm not sure if anyone else is going to talk about this in any detail. At interstellar temperatures, say 100 Kelvin or less, when hydrides are involved, the kinetic energies of atoms and molecules in the gas are comparable to or smaller than the differences in zero-point energies or a deuterium substitution. And what this means is that you can have simple chemical reactions, deuterium exchange reactions, that are the dominant source of the deuterated form of the molecule that will go only one direction at low temperature, okay, because the interstellar gas is too cold for it to go back the other direction. And what that means is that deuterium can become enhanced in abundance in some deuterated forms of simple hydrides and other hydrogen or deuterium-containing molecules. And as a result, most of the deuterium-containing molecules that are observed in interstellar gas are things where the apparent deuterium to hydrogen ratio is maybe as high as 1% or a tenth of a percent. Whereas the overall deuterium to hydrogen abundance ratio in all forms is about 1.5 times 10 to the minus 5. Okay, so these molecular ions like argon H+, are unlikely to have any temperature-sensitive fractionation process. That is, the deuterium will not be enhanced, and the relative abundance of the deuterated form is likely to be 10⁻⁵ of the main form and therefore undetectable. That would be the expectation. Now, I hope someday, eventually, that we might have full coverage in frequency space, where at least we'd be able to put a limit on it, but at the moment, not yet. But potentially it would be observable, the deuterium argon plus. But I've given you an extended footnote.
I would say in that context, are you going to mention the isotopic species of argon that was found?
Yeah,
I think
well, that's
useful.
the embarrassing story.
Yeah. Well, I'm sure the students would definitely want to hear it.
Okay, yeah. Obviously, I'm not going to get all the way through radiative transfer today. This is a really interesting story. Argon occurs in two main isotopic forms. It's there are actually three stable forms, mass 36, 38, 40, as I recall. Now, it turns out that the argon in the Earth, that is the argon that is most frequently found in laboratory experiments, has been produced by radioactive decay near the Earth's surface somewhere in some mineral and then is outgassed or whatever. Okay, so there's one isotope of argon that is the most abundant on Earth. It turns out that the formation processes, the nucleosynthesis processes through stars and supernovae that produce the argon in space favor one of the other isotopes. And that means that you can't just go to Slavalog for the most commonly recorded form of the argon H+ spectrum and expect to find that in space. It turns out we now know with hindsight. Well, the discovery came about because Mike Barlow and his collaborators at University College London were looking at Herschel Space Observatory spectra of the Crab Nebula, and they found some spectrum lines that were unidentified. And the Crab Nebula is the remnant of a supernova that was observed as a bright guest star in the year 1054, and has left behind an expanding gaseous remnant. It has filaments, molecule-containing filaments in it, amazingly enough, even though it's an extremely hostile environment, bombarded with electron cosmic rays that are produced in the wind nebula of the pulsar, which is the collapsed remnant of that supernova. So, in any case, turns out there are molecular ions in the filaments in the Crab Nebula. And so Mike Barlow and collaborators, based on these low-resolution spectra, there were three instruments on Herschel. One was a high-resolution heterodyne instrument. We heard about heterodyne instruments last night. One of the other instruments was a Fourier transform spectrometer, a low resolution, about 1 gigahertz resolution. But still, it's marvelous if you're looking at some part of the electromagnetic spectrum in space for the first time. There are still things to be discovered there at that sort of resolution. And so Mike Barlow was clever enough to realize that since he had two transitions, I think, that the harmonic ratio between the frequencies agreed with the, I guess it was the lighter isotope log of argon H+, by comparison with the tabulated, terrestrially observed isotope log of argon H+. And he said, well, yeah, of course, that's it. And it turns out that I had been involved in a project using the heterodyne instrument to study these absorption lines of reactive molecular ions, right? And we had been struggling to identify an unidentified absorption line in the interstellar medium. We didn't know what it was, and I already realized that it was sort of fairly close to the frequency of the tabulated frequency of argon H+, but not close enough at all. But I wasn't smart enough to realize that to realize that the argon in the laboratory wasn't the same isotope as the argon in space. So we had to wait for Mike Barlow to figure it out, publish that result, and then immediately we did the identification of our absorption line. So it's common in the galactic interstellar medium, and actually quite interesting, because it tells us something about a narrow part of parameter space in the diffuse neutral interstellar gas. The part of parameter space where the molecular fraction of hydrogen in molecular form is actually quite low, and sort of characteristically of the order of 1% or less. That's where the argon H+ is. There's a little bit of molecular gas in that component, and those conditions are especially favorable for the argon H+. Okay, well, I was going to tell other stories about also why ultraviolet spectroscopy is of interest. Let me zip through this quickly. The long story is that together with Fred Chaffee and Craig Foltz, who were both at the University of Arizona at the same time as I, in the 1980s, tried with the best state of the art at the time to detect molecular hydrogen, redshifted molecular hydrogen at high redshifts toward quasars by looking for the redshifted ultraviolet lines, the well-known ultraviolet of the electronic spectrum of H2, without success until finally in 1988 we came up with a fairly convincing confirmation. There had been an earlier suggestion that had been based on less accurate spectra and simply doing a correlation analysis between a laboratory line list and a list of absorption lines. Now, the thing about these quasar spectra, in the upper right corner, I'm not going to try to risk pushing the laser pointer again because it tends to take me to unknown parts of the talk instead of the slides, or maybe I should use my finger rather than the thumb. But in the upper right panel, there's a spectrum that's not all noise. Most of those features are actually absorption lines. There's one extremely broad one, which is in the lower subpanel, the Lyman alpha resonance line. The Lyman alpha resonance line of atomic hydrogen that appears very strongly. That's the way that we pick out the most favorable redshift systems for looking at the molecules. And in fact, more of the Lyman series can be picked out easily enough, but all of these hundreds of other sharp lines are actually also atomic hydrogen Lyman alpha at many different redshifts. It's called the Lyman alpha forest. It's a veritable forest of hydrogen gas clouds spread throughout intergalactic space, all the way up to the redshift of the background quasar itself. Well, in any case, to make a long story short, instead of just comparing line lists, by making synthesized predicted spectra and of the expected behavior of something like interstellar H2, and shifting those around, we found sufficiently convincing matches that we were fairly secure about the identification, and in fact already could estimate the column density of hydrogen molecules, about 10 to the 18th per square centimeter. In comparison, these antique spectra here, only 1 angstrom resolution, a few hundred kilometers per second velocity resolution. In comparison, in the upper left panel here are some modern spectra obtained with an 8 meter class telescope, a marvelous near UV visible spectrograph at the European Southern Observatory. Now it's possible to resolve multiple Doppler velocity components in these molecular hydrogen lines at a redshift of z equals 2.8. But in fact, we got the number about right for the column density as well. Anyway, so I've been interested in trying to look for molecules at high redshift for a long time. One other more recent development is that there are gamma ray bursts in distant galaxies that produce afterglows, and they really disturb the interstellar medium of the host galaxy in which the explosion goes off. But briefly, that afterglow produces so much ultraviolet light that it can be seen redshifted all the way to us as a bright enough visible light background source so that the interstellar medium of the host galaxy of the gamma ray burst can be probed by absorption spectroscopy. And this is a case where the UV spectra of both carbon monoxide and molecular hydrogen have been studied at a redshift of 3 now. That's very far away, even by the current standards of extragalactic astronomers. So now, oh dear. Yeah, I did get a late start, I think. In any case, okay, maybe I should summarize this part of the talk by saying that carefully prepared and very extensive detailed notes have already been posted, both in slides and 40 pages of text and equations. So I don't know how, could I take 5 more minutes?
Sure.
Just to get started on this, I'll probably continue a little bit of it in the third lecture tomorrow. But I wanted to provide you at least with a little bit of background about the theory of radiative transfer, which means both how an electromagnetic signal is processed in the source, in the astronomical source. And of course, a simple absorption spectrum is often very straightforward to analyze. And Mike touched on this in his lecture just a few minutes ago, because in the laboratory often you try to do absorption spectroscopy and it can be simple to analyze. But in astronomy, we don't get to choose, what experiment nature has set up for us. So we often have to try to learn how to analyze both non-equilibrium emission spectra as well as simpler absorption spectra. So the whole point of this is to understand how the spectrum that we detect here on Earth, after it has emerged from a source and has passed through possibly other things in between, how we can relate the spectrum we observe to the conditions in the source itself. So this involves both being able to write down equations that describe the internal excitation state of the atoms and molecules that produce the spectrum, and also how the intensity of the spectrum is changed as it propagates both through the source itself and through any intervening medium. So I start out in these notes by just defining the specific intensity of radiation, so it's power per unit small area, power striking a small area d sigma in some angle away from the normal to that detector area in some direction in space, emerging from some small unit of solid angle projected on the sky. And the dimensions of this intensity are like this. And then this detected power, in fact, what we actually measure more directly is the spectral flux density of radiation. We see how the flux is related to the intensity. I introduced some things about Planck functions in black bodies. And there's one thing in particular that's extremely useful for analyzing any astronomical sources that can be related to a black body spectral energy distribution. And that is that if you take the function 1 power of frequency times the Planck function, the shape of the spectrum remains the same if you change the temperature of the black body or change the total power of the source by making it larger or smaller. Especially on a log-log diagram, logarithm of frequency times intensity per unit frequency versus the logarithm of frequency. Or you can do exactly the same thing and just flip the coordinates and do a wavelength times the intensity per unit wavelength, as you wish. But the useful thing is that the shape of that curve remains the same under translations in temperature and also in total power. So that's very useful. That's why I bothered to put this in the notes. Then we have the equation of radiative transfer. So we have a geometrical factor, which is the angle with the viewing angle with respect to the normal to the detector, and this is a differential equation. It's how the intensity changes with path length through an absorbing emitting medium. And so there may be emission coefficient, especially if we're observing rotational spectra of molecules where there is enough energy in a low temperature gas still to produce emission lines. There may be a contribution to the emissivity at some frequency nu, but the intensity in the source can also be attenuated by molecules that absorb with some extinction coefficient. And I say extinction coefficient because sometimes we actually have to allow both for scattering of light, usually that's scattering by dust particles, as well as pure absorption in atomic and molecular processes. So that's the equation of transfer. Astronomers normally go from that form, how the intensity changes with path length through the source gas, to a dimensionless length scale called the optical depth. And the optical depth is just the integral of the extinction coefficient over path length. So formally, that's what optical depth means. You've heard the term several times already. There's also a thing that people who do formal radiative transfer refer to as the source function, which is the ratio of the emission coefficient to the extinction coefficient. And so the equation of radiative transport, that is how intensity grows or diminishes through the column of gas, can be rewritten in terms of this dimensionless optical depth in this form. And so everything basically in spectroscopic analysis refers to models that have to do with solving that equation of transport or radiative transfer. Then we get to how the absorbing or emitting properties of a molecular gas are related to the emission coefficient in some form. And that's what all of this is about. Susanna actually already covered a lot of this, but I did want to show an example of what a high-resolution spectrum in the far ultraviolet looks like. This is a wavelength of 1,000 angstrom units, or 100 nanometers. So in the far ultraviolet, this is exactly the part of the spectrum where both atomic and molecular hydrogen have very large absorption coefficients in electronic transitions. And so that's what this is showing. This is the extinction cross-section for H and H2. That's all pure absorption. This becomes flat here at the ionization limit of atomic hydrogen, just here. So this is the calculated spectrum for an equal mixture of atomic and molecular hydrogen gas at low temperature, as we might see it in the interstellar medium, or as an ultraviolet starlight photon might see the interstellar medium if it's trying to plow through it. This is the wavelength dependence of the absorption coefficient. So it's very high and constant in the ionization continuum of atomic hydrogen, and then all of the individual lines produce these sharp spikes. And down here, you see something that's starting to rise up, and this is the extreme wing of the Lyman alpha, the principal resonance line of atomic hydrogen at 1215.67 angstrom. Okay, so as I said, this is what an interstellar cloud of hydrogen looks like to a starlight UV photon. In more detail, it looks like this. And in the red curve, I've added the absorption coefficient at about the same wavelength region here, 1,000 angstroms. In red, I've added one of the ultraviolet bands of carbon monoxide. Now, these are important to understand, even if you never worry about ultraviolet observations in astronomy. This is still important for interpreting the meaning of interstellar gas clouds that produce millimeter wave emission lines, because these are exactly the spectroscopic features that determine the extent to which carbon monoxide survives dissociation by ultraviolet starlight, and also determines the boundary between the atomic and molecular hydrogen in the parts of molecular clouds that are exposed on their surfaces to ultraviolet starlight. So this is extremely important in the interpretation of interstellar chemistry in any region where ultraviolet starlight is illuminating the surface of a molecular cloud. So that's really all the time that I have to go through this part. I still have one lecture left tomorrow, so I can resume with some of this. But again, all of this is in the notes, but I wanted to get a start on it to tell you why I think it's important. Okay. I'll probably be out of breath on the hike, but you can ask me questions.
Also, are there immediate questions that anybody may have? If not, then let us take a very short break. If you have also personal things to ask. So let's take a 2-minute break and we'll come back.
Yeah. So far, this question came up actually. Important triggers for things.
We're using all of our
No, I didn't. this, like,